Okay, so I'm going to start. Well, I'm first of all, please tell me if you have any question. If you have any question about the the exercise for Unit 3, about the exam, about any of the topics that we have covered, about the grading or something like that. Is there any question? No? Okay. Okay. In any case, please feel free to interrupt me if you have any question. And what I'm going to do is to solve some exercises from the exam that I have uploaded to the virtual campus. Okay, this is an exam from several years ago, and this is, well, somewhat similar to what you may expect in the final exam. Okay, with some exercises of each of the units that we have covered. Okay, so I'm going to solve the exercises that are directly related to graphs, and then I'm going to go to the worksheet for Unit 3 to solve some more exercises on graphs, unless you want me to solve the other exercises that are on this exam, which are about automata and grammars. Okay, the people from the other seminar chose the the exercises on the worksheet, and that session it's recorded, or at least I think it's recorded. So maybe you want to choose the other exercises, and you can watch the other session. Well, after I solve the exercises on graphs, you can decide. Okay. Uh, okay. So the first exercise is about Hamiltonian graphs and Hamiltonian circuits in graphs. So remember that I told you that finding or checking whether a graph has a Hamiltonian path or circuit, it's not easy. Okay, we do not know of any efficient algorithm, any algorithm that runs in a sensible time, depending on the number of vertices and edges of the graph, that checks whether a graph has a Hamiltonian path and finds the Hamiltonian path in that case. This is what we call an NP-complete problem, and we strongly suspect that there is no efficient algorithm to solve this problem. Okay, so if I give you a graph and I ask you to find a Hamiltonian circuit, or if I ask you if there is a Hamiltonian circuit or path in the graph, then you must be in one of three cases. It either is one of the situations in which we know how to solve this problem, which is mainly for complete directed graphs for tournaments, or it is very easy to find the Hamiltonian circuit or path, or it is very easy to show that there is no such a path. Okay, so let's see what's the situation in this first exercise. I'm copying the graph in the whiteboard, and please take a look while I copy the graph to see what is the situation here. Okay, just the names of the vertices remaining. Okay, so this is the graph. Okay, and clearly this is not a tournament. Okay, for starters, this is not directed, and there are no connections among all the different vertices in the graph. So this is not complete, and we cannot use the algorithm that we have studied in the lectures. Okay, so it is either very easy to find a path, or it is very easy to show that there is no such a circuit in this graph. And here notice that if there were a Hamiltonian cycle or any cycle in this graph, then it would have to use these edges here. Okay? Because when I go to 5 with a cycle, I need to go out of 5. Okay, and there are just 2 edges connecting or incident in 5. Okay, and the same is true for 4. If I have a cycle, I need to go to 4 and back and go out of 4, and for that I need to use the 2 edges that I have in 4. Okay, so these edges must be used in any cycle in this graph. Okay, and then it's after I have located this, identified these edges that must be in any Hamiltonian circuit, in any Hamiltonian cycle. It is very easy to check that we can complete the cycle like this. Okay, so in this case it was very easy to find the Hamiltonian cycle, which is 1, 2, 5, 6, 4, 3, and then back to 1. Okay? Another situation that we could have is a graph in which it's very easy to see that there is no Hamiltonian cycle. For instance, something like this. Okay? Because if start here and I need to start there because I need to visit that vertex, and I cannot get to that vertex with any arrow, then I either go up or I go down. But if I go up, I cannot go back to the bottom of the graph, and if I go down, I cannot go up to the other 2 vertices. Okay, so in this case, it is clear that there is no Hamiltonian path. Okay, so you can have any of these 2 situations. It is either very easy to find the Hamiltonian path or cycle, or very easy to show that it's not possible. Okay, for a general case with many vertices, the problem is not trivial. Okay, the problem is can be very, very difficult. But in the exam, if you have a question like this one, it will be something similar to this. Okay, any question about this exercise? No? Okay, then let's focus on exercise 2. Okay, I don't know if you can see this very clearly. Okay, so here we have to draw the binary tree that corresponds to this arithmetic expression, which is in fixed notation. And after we have found the binary tree, we need to traverse the tree in post order to obtain the postfix notation for the expression. Okay, so let me quickly copy the expression, and then I go to the whiteboard and I draw the binary tree. Okay, so in order to write the binary tree, we need to find at each step the weakest operation, which is the last operation that we compute in the expression. And here, because of the brackets, clearly the last operation is this multiplication, and then we have this part and this part of the tree. So here we have a division with 9 and 3, and then here addition because of the brackets, and then this multiplication and this subtraction. So 2 and 4, 7 and 6. Okay, any question about how to obtain the tree? No? Okay, so now I compute the post order notation for the expression, the postfix notation, by doing a post-order traversal of the tree. And in the post-order traversal of the tree, remember that I first visit the left subtree, then the right subtree, and at the end, only at the end, I visit the root. Okay, and I do that recursively. So when I go to this left subtree, I do the same. First left, then right, then the root. So 9, 3 division. Okay, now I go to the right subtree, and there I recursively apply the post order algorithm. So left, right, and then the root. So 2 for multiplication, okay, because I apply again the post order in this subtree, then post order in this subtree, so 7, 6 minus, then the root, and then the root of the whole tree, which is this multiplication. Okay, and this is the postfix notation for the expression. Notice that this division goes with these two operands, this multiplication with these two operands, so this is a unit in itself. This subtraction goes with those two operands, then this addition with these two operations there, and finally this multiplication with the addition and the division here. Okay, is it clear? Any question about this exercise? No? Okay, very good. So please now tell me what you want me to do. I can either keep on solving the exercises on this exam, or I can go to to the worksheet of Unit 3 and solve some exercises here. That is what I did in the previous seminar. Okay, so please tell me if you want me to do something different or the same. The other session, I think it's recorded. I will upload it to YouTube. But if you want me to solve the same exercises for you to be able to ask questions, I'm also okay with that. Okay, so what do you prefer? I only see 4 people here. I don't know if there are other people connected. Okay, so let's vote. I don't know where's the here. So please tell me or write in the chat what you want, exam or worksheet. Worksheet. Okay. 3 to 1. Okay, sorry, Sebastian. Sebastian is changing. There are more people here. Okay. Okay, any other vote? Well, okay, so 3 to 1 or 3-0. Okay, for worksheet. Okay. So, let's I will solve maybe a different exercise. For instance, in the previous seminar I solved 8, which is similar to 4. Here I will solve 4, so we can you can also watch the other one if you want, but it's the same because it's computing the reachability matrix. Okay, and if anybody wants to have both solutions, it will be possible by watching both seminars. Okay, so here we are asked to compute the reachability matrix for this graph. Okay, in order to do that, let me copy the graph. We need first to compute the adjacency matrix. Okay, I'm copying the graph. 5. Okay. And let me now move to here. Okay. First, I need to compute the adjacency matrix, and this is something that I can do just by inspection, by checking which edges are present in the graph. Okay, so for instance, from 1 I can go to 2 and to 3, but not to 4 or to 5 directly. Okay, from 2 I can go to 1, to 3, and to 4. From 3 I can go to 4. Okay, 4 has no arrows, and 5 can only go to itself. Okay, as a sanity check, I can count the number of ones in the graph. Sorry, the number of ones in the adjacency matrix, and that must be exactly the number of edges in the graph, because this is a directed graph. Okay, in an undirected graph, each arrow gives rise to 2 ones in the matrix. But here, since this is directed, each arrow corresponds exactly to 1 1 in the matrix. Okay, so I have 1 2 3 4 5 6 7 edges, 1 2 3 4 5 6 7 ones. Okay, so this is a way of checking whether I'm missing something. And this matrix is what we call the adjacency matrix, and also the one order reachability matrix, the matrix that tells us what are the paths of length 1 in the graph. Okay, and you know that in order to compute M2, I need to compute the square of this matrix. I need to multiply this matrix times itself. So I'm copying the matrix here in order to make the multiplication. So 0 1 1 0 0 1 0 1 1 0 0 1 0 0. Okay. And remember that, let me see if I can fit it here. Yeah, I think so. Okay, so in order to obtain the result of the multiplication, I can do the regular multiplication and then transform any number which is bigger than 1 into 1. But I can do it more quickly if I remember that this is Boolean multiplication, and then when I multiply, for instance, this row times this whole matrix here, the only thing that is important is the ones. The zeros will have no influence, okay? And this one here is going to multiply this row here, while this one here is going to multiply this row here, okay? So what I'm doing when I'm multiplying that row times that matrix is summing up the second and third row, because I have a 1 in the second and third position. Okay, so I can do it more quickly if I just focus on the ones and on the rows that the ones are affecting. Okay, so in this case, this means that for the first row I only need to sum up the second and third, and the sum of the second and third is 1 0 1 0. Okay, remember that this is Boolean addition. So what we are doing is the OR of the elements. You can consider 0 as false, 1 as true, and then 1 plus 1 is true or true, which is true, which is 1. 1 plus 1 is 1. Okay, so this first row should give us the paths of length 2 starting from 1. Okay, let's see if that is correct in the graph, and we see here that from 1 we can go to 2 and back, okay, with a path of length 2. So this is what we have obtained here, this number, this 1. We can also go from 1 to 2, then to 3. So this is why we have a 1 here. We can go from 1 to 3 and then to 4. This is why we have a 1 here. And in fact, we can also go from 1 to 2 and then to 4. And that's why we had 2 ones here that added gave us 1. Okay? If we were computing this multiplication with integer numbers, we would have obtained 2 here. Okay? Because there are 2 paths of length 2 from 1 to 4. Okay, but we are focusing now on the binary matrix, on the Boolean matrix, and then we perform Boolean operations. Okay. For the second row, we need to add the first row, the third row, and the fourth row. Okay. Because we have ones in positions 1, 3, and 4. Okay, so we obtain we obtain 1, 1, 1, 1, 0. Okay? No, sorry. I'm computing what is 1 and 3. Sorry. So 0, 1, 1, 1, 0. Okay. This is now the paths that go from 2 with length 2 in the graph. So I have this path here to 3, this path that goes back to 2, and for instance this path that goes to 4. Okay? Yes? Okay. Now the third row. The third row is just a copy of the fourth, but the fourth is all zeros. And the fourth is all zeros again. Okay, no 1 on the fourth row. And the fifth row is a copy of the fifth. Okay, so it's all zeros except a 1 in the last position. Okay, because from 3 there are no paths with length 2, from 4 there are no paths at all, and from 5 I can do this cycle this loop twice to remain in 5. Okay, then this is M2. Okay, and then M3 is M2 times M1. So let me copy here M2. And M1. One, 1, 0, 0, 0, 0, 1, 0. All zeros here. And 0, 0, 0, 0, 1. Okay. Let's write it there. Okay, so now we do the same, but let's try to do it a bit more quickly. Okay, so for this row we have ones in positions 1, 3, and 4. Okay, so it's it's 0, 1, 1, 1, 0. Okay. For the second one is the second plus the third plus the fourth. So it is 1 0 1 1 0, and these other two are zeros, and the last one is again a 1. Okay, so let's check that this is correct. For instance, let's see what are the paths of length 1 from of length 3 from 1. So I can go to 2 to 1 and back. So that's why I have these two here. I can go from 1 to 2 and to 3. So this one here. And I can also do 1 to 2 to 3 to 4. So this one here. And of course I cannot go to 5, and I cannot go to 1 because for that I would need an even number of arrows. Okay, so let's compute M4, which is M3 times M1. So 0 1 1 1 0, then 1 0 1 1 0, all zeros here, and the 1, and then I compute that times 0 1 1 0 0, 1 0 1 1 0, 0 0 0 0 1 0, all zeros, and then all zeros and 1. Okay, so this is again the sum of rows 2, 3, and 4. So that is 1 0 1 1 0. What is that correct? Yes, okay. And then the first and the third and the fourth, which is 0 1 1 0 1, and these are zeros, zeros, and ones. Okay, so these are the reachability matrices for orders 1, 2, 3, and 4. That is what we need in order to obtain the complete reachability matrix, which is the Boolean addition of all these matrices together with the identity. Okay, because remember that M0 is the zero order reachability matrix, the matrix that gives us the paths of length 0, and the only paths of length 0 are those that stay in a given vertex. Okay, so those are the paths of length 0, and then we have the identity matrix. Okay, so we need to add all these matrices in a Boolean way together with the identity matrix that will give us ones in the main diagonal. Okay, so what we obtain is 1 1 1 0. This one comes from the identity matrix, and these two second ones come, for instance, from here, and the fourth one comes, from instance, from here. Okay, so we compute the addition, the Boolean addition, and whenever in a position there is a 1 in at least one of the matrices, we will have a 1 in the final matrix. Okay, sorry, please let me drink a bit of water. Okay, for the second row we have again 1 1 1 1 0, because we have ones here in this matrix, and the one in the second position comes from the identity, from M0. Okay? For the fourth row, we obtain 0, 0, because you can check that all the matrices have zeros at those positions. Okay? And in the third position, we obtain a 1 because of the identity, and then a 1 here because this 1 that we have here. Okay? And here a 0 because that column is always 0 in all the, that position is always 0 in all the matrices. Okay? For the fourth one, notice that all the rows are zeros, but in the identity matrix we are going to have a 1 in this position. Okay? So that is a 1 and the rest are zeros. And the fifth row is always 0, 0, 0, 1, so that is what we obtain here. Okay? And this is the final reachability matrix, which is telling us that 1 and 2 are mutually reachable. So they are in a strongly connected component. Okay? You can go from 1 to 2 and to 2 to 1. Okay? And then you can go from 1 and 2 to 3 and 4. Okay? That is this part here, of course. And you can go from 3 to 4, but you cannot go from either 3 or 4 or 5 to 1 and 2, okay, or from 4 to any other vertex that is not 4, or from 5 to any other vertex that is not 5. Okay, so this is the information that we obtain from the reachability matrix. Any question about this exercise? Okay, perfect. So exercise 8 is similar. Okay, exercise 8 is similar. So please try to do it. Well, in the exercise 8, you are only asked to compute the adjacency matrix, but in the other seminar, I computed the reachability matrix. Okay, so you can try to do it on your own to compute the reachability matrix, and then check in the other seminar the answer. Okay, if you want to do that. Okay. So now I'm going to solve exercise 5. So the idea here is that we have a tree with 50 edges. Okay? So I'm going to write here the information that we have. We have that the number of edges is 50. Okay? We also know that this is a tree. And in a tree, remember that we have a property. You can check it, for instance, in this case, but well, it's true for any tree. We have proved that the number of edges is equal to the number of vertices minus 1. Okay, so here, for instance, we have seven vertices, and you can check that we have exactly 6 edges. Okay, so this is something that is true for any tree. Okay, so we immediately deduce that the number of vertices in this case is 49. Okay, I'm writing this information because the problem will ask us about this kind of thing. Okay, now they tell us that when removing an edge, we obtain from the tree, we obtain 2 trees, T1 and T2. Okay, again, this is something that always happens. If you have a tree like this one, okay, and imagine that you remove that edge, then notice that you find exactly 2 trees. Okay, but this is something that we have proved in general. When you have an edge, if you remove when you have a tree, if you remove an edge, you obtain exactly 2 trees. Okay, and in this case, we are calling these trees T1 and T2. Okay, so we are going to have edges E1 and E2, and since T2 and T1 are trees, we know that E1 is going to be equal to N1 minus 1, and E2 is going to be equal to N2 minus 1, because these are trees, and this is true also always for trees. Let me write this like a better one. Okay. And another piece of information that we are given is that the number of vertices in T1 is equal to the number of edges in T2. Okay? So N1 is equal to E2. Okay? The number of vertices in T1 is equal to the number of edges in T2. And we are asked to find the number of vertices and edges of each tree, T, T1, and T2. And, well, of course, we already know the number of edges and vertices in T, and we want to find E1 and E2. Okay? In addition to this information, we also know that the number of edges of the first tree plus the number of edges of the second tree is equal to 49. Okay? Because the number of edges is now one less than the number of oh, this is, sorry, this should be 51, of course, because the number of edges is one less than we had at the beginning, because we have removed an edge. Okay, so the number of edges of T1 plus the number of edges of T2 is 49. And we also know that the number of vertices in total is 51. Okay, because we have removed no vertices at all, so the total number of vertices is still 51. Okay, and with this we have enough information now to find E1, E2, N1, and 2, and you can do it in many different ways. You have there a system of linear equations, so you can try to use any of the methods that you know to solve this kind of system. But in this case, I think the easiest way is to use this identity here. Okay, so we have that then N1 is equal to N2 minus 1. Okay, I substitute E2 with N1. Okay, and then I use this in this equation to obtain N2 minus 1 plus N2 is equal to 51. So this is 2 times N2 minus 1 is equal to 51. So N2 is equal to 26. Okay? And from this I obtain, so let me write it here, N2 is equal to 26. From that I obtain E2, which should be 25, and I obtain N1, which is equal to E2, which is again 25, and then E1 is one less than the number of vertices, and it is 24. Okay? So this is a way of solving this exercise. You can do it in a different order, but you will obtain the same solution. Okay? Any question with this exercise? Well, let me keep it here. Any question? Okay. So let me summarize what we have already solved in this worksheet. So the first three exercises are very easy, are just about drawing graphs. Okay, so for instance here students in a class, they are the vertices, uh, and an edge joining pairs of students who were acquainted before the course. What type of graph is this? Well, these are very easy questions. Please take a look, and if you find any problem with that, email me, okay? But they are so easy that I'm not going to solve them now because there are other more interesting problems, okay? So 4 we have already solved, 5 already solved, 6 is similar to 11, which we solved in one of the previous seminars or lectures. So let's go to 7. 7 is different. It's a bit more interesting. Okay? So here we are asked to either construct graphs with the properties given in the exercise, or to show that it's not possible to do that. Okay? In all the cases, we need to obtain graphs with 5 vertices. Okay? 5 vertices. And in the first case, we need an Eulerian cycle and also a Hamiltonian cycle. The Eulerian cycle must be also a Hamiltonian cycle. So remember that the Eulerian cycle uses all the edges once and only once. The Hamiltonian cycle uses all the edges once and only once. So we need 5 vertices. And in order to do that, I can just draw a graph like this one, okay? Because in this graph, of course, I have an Eulerian cycle which uses all the edges. If I name these vertices with numbers from 1 to 5, the cycle 1, 2, 3, 4, 5, 1, it's Eulerian because it uses all the edges once and only once, and it's also Hamiltonian because it uses all the vertices once and only once. Okay, so this case is very easy. Let's see the second one. In the second one, again, 5 vertices, Eulerian cycle, but now the graph must be two colorable. Okay? So here the trick is to notice that the graph needs not be connected. Okay? Nobody is asking us to draw a connected graph. Okay? So I can do something like this. Join these 4 vertices in a cycle, and then another vertex that is not connected to anything. Okay, and this graph, of course, is two colorable because I can use, for instance, colors red and green in this way to obtain two coloring of the graph, and it's Eulerian because the cycle that goes from 1 to 2 to 3 to 4 and to 1 uses all the edges once and only once. Okay, so be careful because nobody tells us that the graph must be connected. If you try to do a connected graph, then it's not possible. Okay, but with a not connected graph, it is possible. Okay, another solution to this, if you try to do a connected graph that is simple, is not possible. Another solution is to try to do a graph that is not simple, in which you have more than one edge from one vertex to another. So you can do something like this. Okay, and obviously this graph is two colorable. In fact, it's a bipartite graph. And remember that a graph is two colorable if and only if it is bipartite. Okay, so in this case we have a bipartite graph, and we can use a color for one of the parts and another color for the other part. And this is Eulerian because the degree of all the vertices is even. Okay, so these vertices in this part have all of them degree 2, and these vertices in this other part, and this vertex in the other part has degree 8, which is even. Okay, and of course the Eulerian cycle can go like I go to that vertex and return, go and return, go and return, go and return, go and return. Okay, so this can be done, but you need to be careful not to impose too many conditions on the graph. We are not asked in the exercise to do it in a simple way or in a connected way. Okay. So for the third part, 5 vertices with 4 edges, an Eulerian cycle, and it must be not too colorable. Okay. So to solve this exercise, we need to remember another condition which is equivalent to being not to being too colorable, which is not having cycles of odd length. Okay. So if the graph is not too colorable, then it must have a cycle of odd length. Okay. So we have 5 vertices, and for the graph to be not too colorable, we must have a cycle of odd length. But we have exactly 4 edges. We are asked for exactly 4 edges. So in order to have a cycle of odd length with 3 edges, we need something like this. We need a triangle. Okay? Obviously, this graph now is not too colorable, because when we have a cycle of odd length, we need at least 3 colors. Okay? And we are fulfilling 2 of the conditions. Okay, that the graph is not too colorable, and that the graph is has 5 vertices. But now, if we want to obtain the other condition, if we want to include the other condition, we need the other 2 conditions. We need to include a new edge. Okay. And we also want the graph to be Eulerian. And for the graph to be Eulerian, all the degrees need to be even. Okay? But now here we have degrees 2 for 3 of the vertices, 0 for the other 2. Okay? In this case, now the graph is Eulerian. But we need a new edge. If we add a new edge, then the degree of 2 of the vertices will jump in 1 unit, will increase in 1 unit. If, for instance, I add the vertex here, then these 2 vertices will increase the degree to 3. And then we cannot have an Eulerian cycle, because for an Eulerian cycle to exist, all the degrees must be even. Okay? If I include the edge here, then the degree of these 2 vertices increases to 1. So again, I cannot have an Eulerian cycle. Okay? And if I try to do something like this, then I will have a vertex with degree 3 and a vertex with degree 1. Again, it is impossible to have an Eulerian cycle. I can have an Eulerian path, but not an Eulerian cycle. An Eulerian path can be found with exactly 2 vertices of odd degree. But in that case, there is no Eulerian cycle. Okay, so in this case, this is impossible. Okay, any question about this exercise? No? Okay. So exercise 8 is similar to 4. 9 was solved previously. 10 was solved. 11 was solved. 12 and 13 are similar to the one that we solved in the exam. Okay. And in fact, since exercise 8 was a bit shorter than exercise 4, in the previous seminar, I also had time to compute the traversal of this graph. Okay, so maybe you want to check that. It's at the end of the recording. Okay, but these are similar to the one that we solved in the exam. 14 is similar to 10, and 15 and 16 were solved in a previous seminar. So almost every exercise in this worksheet has been solved, or at least you know how to do it because the exercises are similar to others that have been solved. Okay? Any question? No? Okay. Okay. So thank you for your attention. Please feel free to email me with any question that you may have about the exercise for Unit 3 that, let me remind you, is due on the 24th of May. Or any question that you may have about any of the topics that we have covered, or about the exam, or anything like that. Okay, and if you don't have any other question, then we'll meet again on the day of the exam, that it's the 25th, if I remember correctly. Okay? Thank you. Ciao. Bye. Bye. Bye.